Let's continue our study. I know this part is a little bit difficult for you because it's more like mathematics. It's, yeah, you need mathematical knowledge, but maybe you can choose this way. Here, let's say you can do it if your mathematics is good enough. You can use what you have learned about total derivative. Total derivative is equal to the local derivative plus the convective derivative. You can do that way. And if you can't understand this, you can follow the derivation in mathematics. So maybe we can do this way. Let's go back to the previous slide. It's in differential form, and later we will introduce in the integration form. It will be easier. You see here, I need to record. You see here, for this spring con, we will say the mass of the system will not change with time, right? This one is easy to follow. Mass conserved for the system. We always say mice cannot produce, cannot reduce, okay, without reason. Okay, so for here, this for the mice, for the system, the mice is conserved. However, if we consider the control volume, we'll say the boundary of this control volume actually is the same with the spring boundary. Okay, so you say some remain at the saving, some go out of the saving, right? Some stay inside the saving, right? This is some perfume still inside the spray can, and some perfume go outside the spray can. And so the system, for this system, we have two parts. One is what happened inside the saving, right? What happened inside the saving? Some spring can stay in the saving. Some stay inside saving. Sorry, I write down here for the system, the mice should equal to two parts. Some stay inside the saving, some go out of the saving. Go out of the saving, we know should be the convective terms, right? Some, you see, inside and go outside. Nothing. That would be the total of the system. That's will be total mass of the system. So that's why we have two parts. One, what happened inside the other, what happened through the boundary of the control surface of the control volume. That's what happens through the control surface of the saving. Okay, right. From this one, I think it will be easier to understand. For the mice, for the mice of the system, actually, we need to consider two parts. First, part one will be what happened inside the saving, what still stay inside the spring can. The other should be what happened for those go out of the saving through its control surface, right? So you can write down this mass conservation, or we call it continuity equation in differential form, or we can write down its integration forms. Okay, for integration forms, maybe I think it's easier for you to understand. Okay, so the continuity equation for total flow. Okay, so just now, as we said, what happened inside the CV plus what happened through the control surface of the CV should equal to what happened for the system, right? Or for the mass, we know the rate of increase of mass in CV will equal to net flux influx of mass through the control surface. Here we need to add through the control surface. And so here we have its integration forms. We use this one, it will be easier for you to follow. So first we calculate the mass inside the control volume. This is for differential element. The volume for the differential element times density will be the mass for the differential element and integrate over the control volume and then take the time derivative. So this one actually corresponds to the mass change rate inside the control volume or the mass change rate inside the spring kind. And this one is actually some go out of the spring can, some go out of the control volume through its control surface. And the volume flow rate or the mass flow rate we can calculate. So here we got the control surface for differential element area. We can calculate its volume flow rate or the fluid flow the fluid volume flowing the differential element per unit time times density. This will be the mass flux for the differential element and then integrate over the control surface because for the spring can just go out of the control volume. But for maybe you got a little also some or foam also can go inside the spring can, right? So some go in, some go out. So we need to find out the net flux, net mass flux, because of the fluid flowing the control volume. Okay, so here, two parts inside the control volume and through its boundary or through its country surface, and also the mass go in or go out. And for this equation, because the total mass of the system will not change with time, so the sum of the two terms will equal to zero. Okay, so we got this mass conservation or continuity equation of total flow. And it can write down this way. We say if the mass inside the CV increased, definitely the mass through the control surface should decrease, right? Some go up and the other should go down. That's why its total will go to zero. Okay. If flow is steady, what we mean flow is steady? We mean the flow field will not change with time. So what happened inside the control volume will be a constant. That means it will not change with time. If what inside the control volume will not change with time, so what happened through the control surface of the control volume, it also should equal to zero, right? That means the volume flow rate or the mass flow rate over the control surface will be equal to zero. For steady flow, that means how many in, how many out. This is what we always said for the pipe flow. I think it's easy to understand for this one. It's said flow. This is a pipe. How many inside this control volume? How many should go out of the control volume, right? This is what we always say. How many in, how many out. And if it's incompressible flow, compressible flow means the density will not change with time. So we will say still inside the control volume, the mass will not change, the volume flow rate will not change. So through the boundary of the control volume or through the control surface, CS here represents the control surface of the control volume. So its volume flow rate will go to zero, will equal to zero. Okay, so again, we can see this how many in, how many out. Okay. If there are several 1D inlets and outlets and also steady flow, uniform velocity distribution, the calculation will be easy because for this, if it's 1D and so it will be easy and it's also the velocity is perpendicular to the control surface. And so we will have U times the area times the density, right? Because it's uniform distributed, okay? So this is for steady and 1D flow, and we will not care what happened inside CV because what happened inside CV is actually is constant. It will not change with time. If one inlet, one outlet, things will be much easier. We will have the area times velocity equal to the area times the velocity at the outlet. What does this one mean? This is the area times the velocity. It means what? This is a volume flow rate across the section, right? This is a volume, this is section 1, this is section 2. This is a volume flow rate across section 1. And this one is the volume flow rate across section 2. Here, we assume velocity is uniform distributed in this area, in this control surface. And also velocity is perpendicular to this. Okay, just one moment, I forgot one thing. Okay, one moment. Sorry, I'm back. Sorry, I forgot my pen. Okay. Just still one moment. I need to get my pencil. If we got one inlet and one outlet, and so we have this simple equation. Yeah, we know how many in, how many out. So this explains the waterfall, okay? This is a waterfall in China. And we know when the river becomes narrowed, the velocity will increase, right? And also for the sink overflow, we can say we can use, you see, we got the sink. For the sink, we got the overflow drain hose to guarantee that the sink will not overflow. Okay. We also for the vacuum, we know it's because the inlet nozzle of the shop vac is very large, and the flow area is really very small because we got how many in, how many out. So we have a large area, the velocity will be smaller, but for smaller area, the velocity will get increase. Let's see some examples so we can understand it better. Fluid flows down a circular pipe of diameter D1 and speed U1. It passes through a contraction to a smaller diameter D2, as shown in this figure. What is the mean velocity in the second pipe? You see, we have this circular pipe, okay? And the diameter at section 1 is D1, and the speed is U1, and also the speed is perpendicular to the section. And it passes through a contraction. That means the pipe contracts to a smaller pipe. We need to calculate the mean velocity in the second pipe. We know how to calculate the mean velocity. We can calculate its volume flow rate and divided by its area will be the mean velocity, right? And how to calculate the volume flow rate through the section 2. We don't know the velocity distribution. So how can we do this? We can't figure out it by extrapolation, but we can use what we have learned today. Today, we have studied mass conservation, or we have studied continuity equation of total flow. For this incompressed flow, generally we talk about incompressed flow because for water, okay, compressed flow, how many in, how many out. Or first we decide the control volume. The control volume, the control surface of the control volume follows the solid boundary. Just we use the dashed line to this way. So the control surface, the section 1 is a control surface. Section 2 is also the control surface of this control volume. Definitely, the solid boundary also is the control surface of this control volume. So the control volume is a closed space, okay, should be closed shape, okay. So we got this CS control surface will be the section 1 plus its boundary plus section 2 plus its boundary. Because we know no flow can across the solid boundary. So we know how many inside to the control volume through the section 1 is equal to how many go out of the control volume through section 2, right? And the volume flow rate through section 1 will equal to U1 times A1. Why we got minus here? This minus because it's go inside. Go inside will be negative. Why? Because we know the definition of the normal direction of the control surface will always go outward. and V dot dA. So cosine 180 degree or cosine pi equal to -1. That's why we always say go inside will be negative, go outside will be positive. Sure, you can use this one. You can use because only we got one inlet, one outlet. You can use this equation. Or you use for the total, for the control volume, what happened through its total control surface, the mass will be 0. Okay. And A1, here you need to be careful. Here we talk about a circular pipe. So its area should be calculated using the definition for a circular. Okay. If we say it's a rectangular pipe and use width, so the A1 will be the diameter equal to D1 times 1, right? If it's a rectangular pipe. Okay, here we talk about circular pipe. Okay, so this one is quite simple. Okay, one inlet, one outlet. Here we got the incompressed state flow. We know it's at section 1, the velocity is given, the area is also given, V2, A2 is also given, V3, we don't know, A3 is go out, it's outflow or inlet, it's inlet or outlet, we don't know. So we need to find out the velocity at this section. Sure, the first thing is to choose control volume. Generally speaking, the control volume will, as we said, control volume is a closed boundary, closed shape, right? So the control volume we choose should be this section 1 plus the solid boundary. For the solid boundary, everything we know no flow can across the solid boundary. So you can ignore the solid boundary. Okay, but we know this, it should be the control volume. And so after you decide the control volume, we know what going through the control surface, the mass should be, the total mass should be equal to 0. And here, because velocity is uniformly distributed over the sections, and the velocity is also perpendicular to the sections. So we know the volume flow rate through each section will be equal to V1. A1, this will be the volume flow rate through section 1 plus this one should be plus or negative, minus, because this is in, right? And this is out, plus V2, A2, plus V3, A3 should equal to 0. If I use plus here, use plus, that means I assume it's outlet flow, right? And if you find out the answer is positive, that means your assumption is right. It is really outflow. If it's negative, that means it's actually inlet flow. So right, this one. So here, according to the mass conservation or according to the continuity equation of total flow, over the control surface of this control volume, the volume flow rate, the sum of the volume flow rate over the control surfaces of this control volume, I just have choosing the control volume and will equal to 0. Here, always remind yourself the flow cannot cross the solid boundary. So even we have the solid boundary at the control surface, but because no flow can cross the solid boundary, so you only have section 1, section 2, section 2, section 3. Okay, and so we got here Q1 in equal to out. You just got one inlet and two outlets. Here you assume it's outlet, okay? And then we can find out V3. and it's outlet or inlet. Here, this is 10, this is 15, right? This 10, this is 15, and actually you will find V3 is actually equal to minus what? Minus 10. So it's actually, this one should be inlet, right? You can assume it's outlet, and then you can check out your assumptions, okay? So just now, the two examples are really, really simple. Why? Because the velocity is uniformly distributed, and it's particular to the cross section, so it's quite simple. Here we got more difficult one. Unit velocity is uniform at AB, and the outlet velocity is distributed as the distribution is given. The U is a function of Y. Delta, this value, this is a constant, is actually AB equal to CD. So we need to find the mass flow rate across the service, across the control service BC of this control volume. So the control volume is given to you. You don't need to decide to choose the control volume by yourself. The control volume is A, B, C, D, A. This is the control volume. It's given. And when for this control volume, we have the control service AB, BC, CD, DA, right? We have this control service. And AB, we know its velocity distribution is uniform. For CD, we know its velocity distribution is a function of Y. Now we would like to find out the mass flow rate across the control service BC. How to find out if we know the velocity distribution along the boundary BC, we can use the definition for volume flow rate or mass flow rate to calculate, right? But here we don't know the velocity distribution along BC. How can we do that? Again, the mass conservation. We know for this steady flow, if not specifically tell you it's unsteady, we assume it's steady flow. For this steady flow, the mass flow rate over the whole total control surface should be equal to 0. So this one is what happened through the control surface. What happens through the control surface will be the total of flow in plus the total flow out will equal to 0. So this one we know, and we got control surface AB, BC, CD, AD. So we got we can calculate the mass flow rate AB, BC, and CD and DA. BC is what we need to find out. This is unknown, right? For AB because it's uniformly distributed. For AB because it's uniform distributed, right? So we can calculate easily, right? It will be equal to the velocity times its area, right? And unit values will be 1. So this will be the velocity because velocity is uniform distributed, and the velocity times the area of the control surface. This can be calculated because the velocity is given and it's uniform distributed. This one is unknown. And for CD, for this one, the velocity distribution, the velocity profile is also given. But here, the velocity is not uniform distributed. You need to calculate the volume flow rate per unit volume flow rate for each differential element and then do the integration, right? And for dA, what will be the volume flow rate across dA? dA is solid boundary. So this one will be equal to 0 because no flow will across the solid boundary. So this is given, this it can be calculated, so we can find out this directly. So we know this one is because it's solid boundary, and this one can be calculated, and this one can be found out by this much. In the mathematics, it's easy to define. We don't need to find the velocity distribution, but we can find this sum. Okay. So for AB, it's easy because for AB it's easy because the velocity is uniform distributed. So velocity times the area, AB is equal to delta. So it's easy. And times density will be the mass into the control volume because it's flowing in. That's why we got minus here. It's very important to keep the signs, whether it's in or out. You should be very careful. And for CD, yeah, be careful. Here it's not uniform distributed. So take the element and then here take the element. We can calculate the volume flow rate for the differential element. For this differential element, this will be velocity and times the differential area. Differential area will equal to dy because here we have established the xy coordinates here. So times dy, unit width will be dy1. And we integrate for the whole city, for the whole section. And so the lower limit or the y will start from 0 to delta. Okay. And then you can calculate the volume flow rate or the mass flux across BC. Okay. So here, the control volume A, B, C, D, A is given to you directly. So you can calculate the volume flow rate or the mass flux through across each control surface, A, B, B, C, or C, D, or D, A. Okay. And a question about this? Let's continue. Let's say now you already found out the flow rate, the volume flow rate, and the mass flow rate, mass flux through control surface BC. How about the volume flow rate across AC? AC, we later on will know this is actually the edge of boundary layer. But anyhow, I would like you to find out the volume flow rate across AC. How to do that? First thing, you need to choose control volume, right? What will be the control volume? Here, how about choose A, D, C, A? Control volume is A, D, C, A. What does it mean? Control volume can be any kind of shape you like. It's up to you. Okay, you can choose a control volume by your wish. So ADCA, and so the control volume is ADCA. So the control surface will be AC, AD, and DC, right? AC, AD, DC. according to the mass conservation, the volume flow rate over the total control surface will be equal to 0. What does it mean? The volume flow rate according to AC is what we need to find out, plus the volume flow rate across AD. It will be 0, right? Because AD is solid boundary. You can choose A, B, C, A. If you choose A, B, C, A, yeah, definitely you can choose A, B, C, A. Let's do it later on. Okay, you choose ADCA, you will find out it will be easy. Here, AC, we don't know, we need to calculate, but you see here, AC plus AD plus CD. I mean, the volume flow should equal to 0, right? And of course, AD, no flow. And so this one equal to 0. And for this one, we can calculate, right? It will be here, right? We just calculate. Even it's not uniform distributed, it doesn't matter. We just need to do the integration. Sure, some students ask me, you can figure out. Some students ask me, how about choose control volume ADCA? ABCA, sorry, EBCA. If you choose control volume ABCA, so you got control surface AB, BC, CA, right? AB uniform distributed. BC just now here. BC just now you already solved. So BC is also given. So you can obtain the volume flow rate or the mass flux through CA, right? So now it's your time. For this question, I think I need to write down here AB equal to CD equal to delta. So you need to know what I mean. So please find the mass flow rate across surface AC. Find the volume flow rate. Please find the volume flow rate across the surface AC. You can choose CV by yourself, okay? But you need to write down your solutions and then upload online, okay? So for this one, you need to find the volume flow rate across the surface AC, okay? So that's all for today. And you need to write down your solutions and then upload online through the WeChat group, okay? See you next week.